So what if the secret to a greener, more sustainable chemical industry was hidden in something as simple as making a sandwich? I know, it sounds a little weird, but stick with me. Today, we're going to unpack a pretty revolutionary idea that starts with, simple ingredients and ends with a totally new way of looking at efficiency and waste.
Okay, let's just dive right in. Picture a chemical reaction. Any reaction. Why doesn't it just go on forever, until every single molecule is gone? What actually puts on the brakes?
Well, the answer is surprisingly simple, and it's something you already get from just living your life. It really is like making sandwiches, right? You can only make as many as your most limited ingredient allows.
It doesn't matter if you have a mountain of bread. Once you're out of cheese, that's it. Sandwich making is over. This very simple idea is totally fundamental in chemistry. It's what determines how much of anything we can possibly make, whether it's in a tiny lab or in a huge factory where millions are on the line.
So this cheese problem, as we could call it, actually has a formal name in chemistry. Chemists don't really talk about running out of cheese. They talk about the limiting reactant, or sometimes the limiting reagent.
So, this is our starting point. This is the official rule for our sandwich problem. It's that one ingredient that calls all the shots. Once it's gone, the reaction stops. The party's over because we ran out of cheese.
Okay, it's one thing when it's bread and cheese, right? But how do you figure out the limit when you've got a beaker full of complex chemicals swirling around? It's a little more complicated than just counting slices, but honestly, the logic is exactly the same.
Chemists said this really elegant way of figuring it out. You basically run a little thought experiment for each ingredient. You ask, okay, if I had an infinite supply of everything else, how much product could this one chemical make all by itself? The one that gives you the smallest number, that's your bottleneck. That's the one that shuts the whole operation down.
And this table here shows it perfectly with a real reaction. Let's say we start with 15 grams of copper 2 chloride. The absolute most salt we could ever hope to make is 13 grams. Now, that 20 grams of sodium nitrate could make 14 grams, but it's never going to get the chance.
So the bottom line is, the copper 2 chloride is in charge. The reaction just hits a wall at 13 grams, and all that extra sodium nitrate is just left over, unused. And this idea? This is what leads us to how chemists used to think about success.
For decades, and I mean decades, the number one way to measure if a reaction was any good was something called percent yield. It was the gold standard. It was like the final grade on a chemist's report card.
And on the surface, this makes perfect sense. If the math says you can make 13 grams of something and you actually get 11.3 grams, hey, that's a pretty good yield. A higher percentage has to mean a better, more efficient reaction, right? Well, what if that high score is just a complete illusion?
Take a look at this. 86%. That's the percent yield for something called the Whitted reaction, which is a total workhorse in making all sorts of pharmaceuticals. And an 86% yield sounds fantastic. That's a solid B+. You'd think this process is a shining example of chemical efficiency.
This is where the whole story takes a huge turn. What if getting a great grade on the test doesn't tell you anything about the giant pile of trash you left behind to get it? This question, it exposes a massive hidden flaw in just looking at percent yield.
And here is that dirty secret. For every 96 grams of the good stuff we actually want, this so-called highly efficient reaction creates a staggering 278 grams of waste. That's almost 3 times more garbage than product, just by weight. That 86% yield suddenly doesn't tell us the whole story, does it?
This quote just nails the problem that was hiding in plain sight for so long. The entire chemical industry was full of these processes that looked great on paper, getting these high percent yield scores, but in reality, they were unbelievably wasteful, creating massive environmental and, frankly, economic problems. So this huge problem, it needed a whole new way of thinking. And in the 1990s, a chemist named Barry Trost proposed a brilliant new concept, a much better way to measure what efficiency really means. He called it atom economy.
So what is atom economy? Well, instead of just asking how much stuff you made, it asks a much deeper question. It asks, of all the atoms you put into the pot at the very beginning, how many of them actually became the thing you wanted, and how many just got thrown in the trash?
So let's look at that same highly efficient Whitted reaction again, but this time we're using this powerful new lens of atom economy. And the picture is, well, it's shocking. It's only 26% atom economical. That means a mind-blowing 74% of the weight of all the atoms we started with ended up as pure waste.
Yeah, that 86% yield doesn't look so hot anymore, does it?
Okay, so it's a great idea in theory, but does this new way of thinking actually make a difference in the real world? Let's take a look at how it completely changed the way we make one of the most common painkillers on the planet, ibuprofen. So the original recipe for ibuprofen way back in the 60s was this 6-step monster. And each of these steps, with their crazy names, needed huge amounts of other chemicals that never even ended up in the final pill. They were just used once and then tossed. Now look at the modern way, the BHC process. It's just beautifully streamlined, only 3 steps. And the key here, the use of catalysts. Think of them like little chemical matchmakers. They help the reaction happen, but then you get them back at the end, totally unchanged, ready to be used over and over again. They generate almost zero waste.
And this chart just says it all. Look at that bar on the left. The old process was just limping along with a terrible atom economy of 32%. Now, look at the green bar on the right. The new process clocks in at an incredible 77%. That means more than double the atoms you start with actually end up as the painkiller, not as some hazardous waste.
And that's the real takeaway here. By just changing the question we ask, by changing how we measure success, we can completely change our impact on the world. The new process for ibuprofen isn't just better for the planet, it's also cheaper and faster to run. It's a total win-win-win. This whole journey we've been on, from a simple sandwich all the way to a smarter way of making medicine, leaves us with one last big question. Atom economy isn't just for chemists, right? It's a mindset. So the next time you hear about some highly efficient process, whether it's in a factory or your own kitchen, just ask yourself, what's the real economy here? Where are all the atoms really going?